Hello everyone, I am Dr. Sunil Shingade and presenting the research on how to carry out the designing of the continuous filtration and drying operations or filtration or drying units which is capable for working out effectively at variable flow rates and at different particle sizes. Flow chemistry is an emerging field in pharmaceutical industries. Therefore, it is need of hour to design unit operations like filtration and drying in a continuous manner. Rate of filtration depends upon the size and shape of the particles. Rate of the drying also depends upon the size and shape of the particles. As the size of the particle increases, the voidage between the particles increases, therefore cake resistance decreases and the filtration rate increases. Similarly, as the particle size increases, the voidage between the particles increases and therefore the moisture released from the bulk of the solid gets removed easily, therefore drying rate also increases. And the other aspect is that as the particle size increases, the surface area per unit mass decreases. Therefore, total moisture absorbed on the surface of the solid particle decreases and therefore the drying rate reduces. But in reverse, if the particle size decreases, then the voidage between the particles decreases and the cake becomes more compact. Therefore, filter cake resistance increases and filtration rate goes down. And if the particle size decreases, then the voidage between the particles decreases and therefore moisture releasing from the bulk solid get more resistance and drying rate get reduces. And the other aspect is that as the particle size decreases, the surface area per unit mass increases. Therefore, total quantity of moisture absorbed on the surface of the solid particles increases and therefore the drying rate increases. Therefore, the system design should be capable for working out effectively irrespective of particle size and irrespective of the flow rates. Size of the particles during precipitation depends upon the hydrodynamic conditions and the concentration of the nuclei. The size of particles during crystallization depends upon the hydrodynamic conditions, and in the case of cooling crystallization, it depends upon the cooling rate, and in the case of evaporative crystallization, it is depend on the evaporation rate, means the rate of generation of nuclei. The design assembly of filtration and drying operation should be capable for working out effectively at different particle sizes and varying flow rates. Because for every time we cannot change the size of the designed equipments, and therefore the design system should be such that it can operate at varying conditions, means at varying particle size and varying flow rates. The system which we have selected is the filtration and drying of calcium oxalate. The calcium oxalate gets formed from the reactive precipitation between calcium nitrate and oxalic acid, and it is an ionistic type of reaction, and the calcium oxalate form exhibits the negligible solubility in water, therefore it gets precipitated out instantly, therefore it is a reactive precipitation type of reaction. Large number of nuclei are getting formed instantly and they are not getting sufficient time to arrange themselves in a particular shape, therefore they are agglomerating randomly and therefore the product form is completely amorphous in nature. The chosen concentration of calcium nitrate is of 1 gram mole per liter, and that of oxalic acid is of 0.5 gram mole per liter. This is the batch experimental setup which we use to carry out the reaction between calcium nitrate and oxalic acid in aqueous media to form the slurry of calcium oxalate, which is necessary to carry out the filtration study and the drying study. The reaction volume is of 600 ml. The molar ratio of the reactants is 1:1. The stirring speed, this means the speed of agitation, was 500 rpm, which was larger than the critical settling velocity of the largest particle. The reaction was carried out room temperature and in aqueous media. From the experiment, it is observed that the mean particle diameter increases over the period of time, and it increases up to 30 minutes, and after that almost it remains constant. From this experimental study, it is also observed that the particle diameter varies with stirring speed. Initially it increases with stirring speed, means speed of agitation. This is because nuclei has to remain in the suspension to agglomerate together and to increase in the particle size. Therefore, particle size increases initially with the speed of agitation, and after that, after a certain limit, it goes on decreasing. This is because at the high speed of agitation, attrition between the solid particles and attrition between the liquid and solid takes place, and the particle size decreases. As the formed particles are completely amorphous in nature, and we consider these are, or we assume these are in spherical shape, and therefore use the Coulter counter to measure the diameter of the found particles. These are the observations of the Coulter counter, and from these observations we have estimated the number of particles present in the different range of particle diameter, and these are plotted against the mean particle diameter, which is called as particle size distribution. Because particle size distribution is necessary if two sets of experiments are carried out, and in both sets mean particle diameter is same, but the particle size distribution is different, then obtained zeta potential must be different, might be different. If the particle size distribution in both sets is same, but mean particle diameter is different, then also the obtained zeta potential varies. Therefore, for getting the same zeta potential for both sets, then the particle size distribution as well as mean particle diameter should remain same. The R1 equation is used to find out the filter medium resistance and specific resistance. The filtration study has been carried out, and the cumulative volume is measured with time, cumulative time, and that is T by V is plotted against V. The slope gives B1, from which the specific resistance alpha can be estimated, and from the intercept the filter medium resistance can be estimated. This is the batch experimental setup which we use to perform the filtration study, and once the filtration study has been carried out, we have estimated the filter medium resistance by knowing the slurry flow rate, input slurry flow rate, the concentration of solid in that input slurry, the specific cake resistance and viscosity of the filtrate, and by assuming filtrate rate is same as the rate of input slurry, the area of the belt filter has been estimated. The area of the belt filter required is to be 25 centimeter per square, but the residence time provided for cake on the belt filter is equal to be 20 seconds. Therefore, the total area of the belt filter to be fabricated is equal to the area swept by the belt filter in 1 second into total time provided for the cake on the belt filter is nothing but equal to the 500 centimeter square. By assuming the width of the belt filter as a 12.5 centimeter, the length of the belt filter has been estimated and it is of 40 centimeter. It has been studied to find out the constant drying rate, the critical moisture content and the equilibrium moisture content. The critical moisture content is such that up to critical moisture content, the rate of releasing the moisture from the bulk of the solid to the surface of the solid should be the same to the rate of evaporation of the moisture from the surface of the solid. And once the rate of releasing the moisture from bulk of the solid to the surface drops below the rate of evaporation of the moisture from the solid surface, then the drying rate falls down. And the typical critical moisture content is called as a critical moisture content is called as a critical moisture content, at which drying rate falls down. The equilibrium moisture content depends upon the surrounding environment. If the humidity in the surrounding environment increases, then the equilibrium moisture content increases. If the atmosphere is dry, means humidity is less, then the equilibrium moisture content will be less. The bound moisture content is such that the vapor pressure exerted by bound moisture at particular temperature T is less than the equilibrium vapor pressure exerted by the free liquid at the same temperature. This is the schematic of the screw conveyor. This is the length of the screw conveyor and this is the cross-sectional area where D is the diameter and we have taken D is equal to 10 centimeter for fabrication. This is the shaded area, shaded cross-sectional area into length gives us the total volume occupied by the solid inside the screw conveyor dryer is nothing but this much. We have derived this equation using the trigonometric equations, and the heat transfer area to the solid material is this cross-sectional curve length into this length L, means this area. By solving these two equations simultaneously, the length of the belt filter screw conveyor dryer has been estimated and it is 1.44 meter. This is the novel part of continuous filtration system, because as we already discussed, the rate of filtration depends upon the size of the particles. It varies with the size of particles and it varies as the input flow rate gets varying. But our system should be capable to work out effectively irrespective of the flow rate and irrespective of the particle size. This is the belt filter and it is connected to the pipe. Pipe is dipped inside the liquid fuel and it is open from the bottom side. The pipe is connected to the vacuum pump and the vacuum adjustable valve is also assembled on this pipe. If we have to increase the filtration rate, then we have to increase the vacuum strength inside the pipe, and this can be increased by reducing the opening of vacuum adjustable valve. And if we have to decrease the filtration rate, then we have to reduce the vacuum strength inside the pipe, and that can be done by increasing the opening of the vacuum adjustable valve. By increasing the opening of vacuum adjustable valve. In such a way, we can manipulate or we can adjust the filtration rate by varying the vacuum strength inside the bed filter by adjusting the opening of vacuum adjustable valve. Similarly, drying rate can be adjusted. If we have to increase the drying rate, then we have to increase the vacuum strength inside the screw conveyor dryer, and it can be done by reducing the opening of the vacuum adjustable valve. If we have to reduce the drying rate, then we have to reduce the vacuum strength, and it can be done by increasing the opening of the vacuum adjustable valve. In this way, vacuum inside the screw conveyor dryer can be adjusted, on which drying rate can get varied. Therefore, our system is capable for working out effectively at different flow rates and at different particle sizes. Thank you. Conclusion of the project of designing continuous filtration and drying operations is as follows. The novel aspect in this project is as follows. This is the continuous belt filtration system. The tray of belt filter is connected to the pipe, which is deep inside the liquid pool, and vacuum pump is connected to the pipe. The vacuum adjustable valve is also connected to the pipe. If we want to increase the filtration rate, then we have to increase the strength of the vacuum inside the pipe, and it can be done by reducing the opening of vacuum adjustable valve. If we want to reduce the filtration rate, then we have to reduce the vacuum strength inside the pipe, and it can be done by increasing the opening of vacuum adjustable valve. In such a way, filtration rate can be increased or can be decreased without varying the sizing or dimensions of the filtration system. If we consider the case of the drying system, the screw conveyor dryer is connected to the vacuum pump, and the vacuum adjustable valve is attached to the vacuum line. If we want to increase the drying rate, then we have to increase the vacuum strength inside the screw conveyor dryer, and that can be done by reducing the opening of vacuum adjustable valve. And if we want to reduce the drying rate, then we have to reduce the strength of the vacuum inside the screw conveyor dryer, and it can be done by increasing the opening of vacuum adjustable valve. In such a way, the drying rate can be adjustable. It can be increased or it can be decreased. We have to increase or we have to reduce the drying rate without varying the sizing of the drying system. Thank you.